Or do I have to click? No, I can't find my cursor. All right, okay. So that is not what I mean by stripe phases. I just thought of putting this slide up since the Euros are coming up next week. So best of luck to England. Let's see if it gets it home this time after all the hype. The stripe phases I will be talking about are found in electronic systems, mostly, such as strongly correlated systems. There are many such examples of phases of this sort. It's been a very prominent topic in the physics of high-temperature superconductors, be it on cuprates or iron-based superconductors. So essentially, what I mean by stripe phase is a certain symmetry feature of the electronic density of the system. So it could be some sort of unidirectional density wave order. So you could, in electronic systems, you could either have electrons forming a Wigner crystal, right, in dilute density. That's the top left over here. And you could get other forms of more exotic spatial symmetries resembling the physics of liquid crystals. For example, you could get electronic density lining up in those continuous one-dimensional patterns. In the bottom left, that's what is known as a smectic, where you have translational symmetry along one direction and broken along the other, and some unidirectional order. You could also have a nematic, where you have full translational symmetry in both directions, but you still have some unidirectional nature or some isotropic liquid-like feature. So this has sort of been the paradigm of what people call electronic liquid crystals. It was first introduced in the high TC context, and since then there have been several review articles along these lines. I will not talk about high TC or electronic smectics or stripes, but I thought just as an introduction, it'd be a nice way to understand what's been done before. All right. Okay, besides high TC, this has also been done perhaps in the more relevant setting for my talk in the quantum Hall scenario, where in higher Landau levels, by which I mean in lower magnetic fields, people have seen that the electronic or the charge density also assimilates into these sort of stripes or bubble-like phases, depending on the filling of your higher Landau levels. This was initial work by Hartree-Fock work by those people in the late 90s. And since then, there has been a rich landscape of such phases in higher Landau levels, and some recent experimental confirmation of these sort of bubble phases as well. These are all fall under the paradigm of electronic liquid crystals, which again, as I mentioned, has been quite a successful paradigm in the theory of strongly correlated systems. And there have been several review articles written on it. You can take a look if you're interested. And also recent spectacular experimental verification. I don't see Ali Aslani here, but his experimental group in STM studies have done remarkable imaging experiments where you could actually image on the electronic scale the conduction and see some orientational order in materials like bismuth. There have been older transport experiments which show some anisotropy between X and Y, which is a signature of these sort of anisotropic phases. And so this paradigm is quite well established. Now, what I want to talk about today is not the electronic analog, but more through the lens of entanglement. Now, as we've heard very nicely in Frank's talk today morning, entanglement is playing a more and more increasingly important role in quantum matter. There have been various concepts which have sort of transformed the way we look at different phases of quantum matter in the classification of short range versus long range entanglement, which are basically based on the depths of unitary circuits you need to connect a trivial phase to that phase. So depending on if you could do it with a finite depth or not, you have short range, examples of which include trivial symmetry broken states or the integer quantum Hall effect, or long range, such as topological order, some examples of which Frank gave today morning. But I will be using a different concept from this body of work known as entanglement measure, which will basically quantify the amount of entanglement that I will be talking about. And I'll make it quite specific what I mean by that. So it's one thing saying I have two things that are entangled. It's another thing trying to come up with a quantity which actually describes in some physically relevant sense just how much entanglement you have. And that's what the role the entanglement measure plays. All right, okay, so I have to close this bar. All right, so before I get into some details, let me just flash the main result. And the main result that I want to be, this cursor keeps vanishing. Right, The main result that I'll be telling you about is some symmetry breaking in the entanglement measure between spin and valley degrees of freedom in a multi-component quantum Hall system. So what I have plotted here on the top is basically a quantity that I will define later on. It's the entanglement measure, which quantifies the amount of entanglement between spin and an equivalent valley degree of freedom in my system. And as I tune some anisotropy parameters in my Hamiltonian, what I see is that there are features that resemble that of the smectic and stripe phases, eventually giving way to a symmetric phase, but in the entanglement measure. And that's the important point. On the bottom left, what I plot here is the charge density. So the systems I consider here are skyrmion crystals in quantum Hall systems. There was talk on skyrmions as well earlier on. I'll be a little more specific on that soon. But I consider a skyrmion crystal which has the square lattice orientation. So the charge density across all the 4 top scans is actually the same. It has this full rotational symmetry on the bottom left here. But when you look at the entanglement pattern, the large-scale entanglement pattern between spin and valley, you see that even though the charge density has this full C4 rotational symmetry, the entanglement pattern breaks this symmetry down to a C2. And then eventually, so you have these continuous one-dimensional lines, which is what we call the entanglement smectic. And then you have these sort of more modulated one-directional lines, the stripe, and then eventually you get back some C4 symmetry, right? So that's the main result, that you have these symmetry breaking ordering features in the entanglement measure, but not in the electronic charge density.
So you can guess that. So it's not in the electronic charge density, but is it in any other local order value charge?
Yeah, so I'll come to that.
Okay.
Yeah. No, you're absolutely right. So it'll be related to some sort of you can measure it by doing some by the pseudospin density in some sense, but you have to incorporate a picture in which the length of the pseudospin vector can fluctuate, and that is captured exactly by the entanglement measure. So I'll be describing that. So sorry, did I see another hand? Okay. All right. Good. So let me come into some of the system-specific details. So I'll be talking about multi-component quantum Hall systems, by which I mean quantum Hall systems in which I have a spin degree of freedom as well as an equivalent valley degree of freedom. So you could have systems such as graphene, where you have spin and valley, or more recent examples of Moiré systems where the pseudospins can take many other forms other than valley as well. And there's been some recent work on this sort of multi-component quantum Hall systems where people have tried to study the phase diagrams of the lowest and first Landau levels and have found a plethora of these spin valley entangled phases. But I will focus specifically on quantum Hall ferromagnetism. That means I will be in the lowest Landau level and I will fill one of the four sub-levels, because I have one spin and one valley. So that gives me 4 sub-levels. I will be filling one of them and then considering the physics in that. And in that, even in that case, depending on your anisotropy, and I will make clear very soon what these U perp and UZ terms are, depending on those values, you have a whole phase diagram in which you can get entanglement between spin and valley, as well as sort of fully spin polarized or fully valley polarized phases. Okay. All right, so, and based on this, again, by Ali Yazdani's group, there have been remarkable imaging experiments where they can actually visualize textures in valley space. In recent experiments in using their STM tools. And this is because in graphene, especially in the lowest Landau level, there is valley sublattice locking. So every sublattice of your honeycomb lattice is attached to a valley. So by measuring electronic densities over sublattice, you can say a lot about how the textures behave in the valley space in this setting. And that's why there has been some recent progress. Okay, so let me go over some technical details first. Now, if I have a 4-component spinner, I'll be working with skyrmion crystals. So skyrmions live in the complex projective space, by which I mean you just have a 4-component complex spinner. The modulus squared of each of those elements sums to 1. So that gives me a CP3 spinner. And I can decompose any CP3 spinner in that form, in the standard Schmidt decomposition, as you do for entanglement, into some 2-component spinners for your spin and pseudospin. And this introduces 2 additional variables, alpha and beta, which are basically your entanglement variables for the spin, pseudospin, in this case, valley entanglement. And you can obtain your local spin and pseudo spin from this by the following procedure. And you get essentially a nice picture to visualize this. Let me just come to that, is through this block sphere representation. So you can describe your spin and pseudo spin by the respective block spheres, and you get a separate SU3 sort of block sphere from the alpha and beta terms. In this block sphere representation, if you have no entanglement, then the spin and pseudo spin lie on the surfaces of your block sphere. That's the standard explanations that you have. However, if you have entanglement, from this formula you can see here that n over here is a unit vector. So if your alpha is actually not, if your alpha is not 0, that means your n or your spin or pseudo spin vector actually contracts from the surface of the block sphere. So spin, pseudo spin, or spin valley entanglement in this sense allows your local spin or pseudo spin arrow in the block sphere to actually explore the entire sphere and not just the surface of the sphere, which would be the case if it was not entangled. And if you have maximal entanglement, which is the case if alpha is pi over 2, then locally the spin and the pseudo spin will vanish because cos pi over 2 is 0, and your entanglement block vector will lie in the plane. All right, so this is the characterization of entanglement that I will be talking about, and a convenient way to measure this entanglement, as I said, these concepts coming from quantum information of an entanglement measure, is that term over here, sine square alpha. So if they are not entangled at all, then you can see that this will give you 0 because alpha will be 0. So that means spin and valley are unentangled. If, however, they are maximally entangled, then that quantity will give you 1. So that gives us a very convenient entanglement measure to characterize just how much the spin and valley degrees of freedom are entangled. All right, so now just some preliminary things before I get to the main result. This was again mentioned earlier on in this conference, so I don't want to get into too much detail. But essentially in a quantum Hall ferromagnet, if you want to add charge, the cheapest way to do so is through this textured object that's known as a skermion, and this has some special properties. It is electrically charged. It's a topological, the topological charge of it is quite a stable object. You can perturb locally through spin waves. The topological charge still remains the same, and this has been very well studied in works over the past 3 decades. What I want to talk about is a ground state configuration of the skermion crystal. So if you actually dope slightly away from just filling one Landau level of these four of the lowest Landau level, what was shown in pioneering work is that these skermions, much akin to electrons in a Wigner crystal, these skermions, because they are charged, also crystallize to form a skermion crystal, which is actually the ground state configuration at filling slightly away from mu equals 1. And that's the scenario that I will be considering. Okay, so now let's delve into some of the model specific details. So as I told you, I will be considering a quantum Hall skermion crystal with a 4-component spinner. So the most general continuous theory you can write down for this 4-component spinner is given by this energy functional. So the first term here is just some general SU4 invariant exchange term that you would have in your energy functional. The second term here comes from the fact that the skermions are actually charged, and you have a topological charge that interacts via the Coulomb interaction. So this is the topological charge term. Now, without the EA term, because you have this spin and valley degree of freedom, you have an approximate SU4 symmetry. You have an enlarged symmetry group. However, in realistic scenarios, and especially in graphene, you have short-range interactions or electron-phonon interactions. Electron-phonon interactions that break this SU4 symmetry, and that's what this EA term captures. And this, again, I will not go into the details of this. This takes this form. This was in pioneering work done by Kharitonov. If you project these interactions down to the lowest Landau level, you have these where MPX, MPY, MPZ are your local pseudo-spin terms, and MSZ is just the spin Zeeman term. Right, so this is sort of the anisotropy functional that breaks your SU4 symmetry, and this we take in as inbuilt into our energy functional. And we will treat these UP and UZ terms as basically free parameters, because given the nature of these diagrams that Kharitonov calculated, there are various details that could change the values of these UP and UZ in the lowest Landau level. All right, and essentially, this energy functional is very hard to do anything analytically. A good way to go about that is to start from an ansatz, and a good ansatz to start is these theta functions to satisfy periodic properties of the squarmion crystal. I don't want to get into too much detail, but essentially, if you impose the limit of this energy functional where your J term or your exchange term is much greater than all the other scales, the requirement for the wave function becomes that it has to be some sort of biperiodic holomorphic function. And to satisfy those periodic properties, an easy way to do that is by using these theta functions. I don't want to get into too much detail. We can describe that. We can discuss that offline if you're interested. But essentially, you start off with a 4-component spinor, psi r, where F is your some random SE4 matrix that you have to parameterize. Details are in the paper. And psi naught r is some basis vectors using these theta functions. Okay, and this, you start off from this, and then you do your standard minimization problems depending on UP and UZ to see what the optimal spin and pseudospin profile is of your squarmion crystal. Now, before I get into the entanglement, let's first try to get a very simple picture as to why there would be any entanglement at all, and in what case. So consider the anisotropy functional that I gave over here, right? And you have these 4 sublevels of your 0 at Landau level, correct? Now, imagine that if I have some condition that requires my spin to be polarized to spin up, that means I can be in one of the 2 top levels. That means my pseudospin has to be either along the easy axis, that can be one option, or it can be in plane. In both cases, if I have UP and UZ positive, I will be paying some anisotropic energy cost, right? Because if I have to fully align along Z-axis to get any sort of Zeeman energy gain from the MSZ term, I will necessarily have to pay some penalty by giving some MPZ or MPX plus MPY term in the in-plane component, right? So entanglement in this spin valley sense allows you a compromise. It says, okay, you can go in plane or you can go easy axis, but what I can do for you is I can reduce the length of your vector, right? So even if you are in plane, you can pay a smaller energy cost if this MPX and MPY becomes smaller than, if your pseudospin vector comes inward from the Bloch sphere. And that's why I wanted to give this Bloch sphere analogy. If you were purely on the Bloch sphere, then you would inevitably pay more energy than if you could contract your local pseudospin vector away from the Bloch sphere. And for certain parameter ranges, this sort of intuitive physical picture implies that your spin and pseudospin get entangled and allows you to do this compromise between aligning in plane or out of plane. Okay. All right. So if you do that minimization procedure that I outlined, what I said again in the main results, that if you fix your UP to be a certain multiple of delta Z, and you tune your UZ, so if you tune your easy axis anisotropy while keeping your in-plane anisotropy fixed, and if you plot the entanglement measure, sine square alpha, you see for low values of UZ, you get these entanglement smectics, by which I mean you get these very bright or maximally entangled lines along in which the local spin and pseudospin vectors essentially vanish, and the entanglement vectors lie along the plane. And then as you increase UZ, these sort of smectics start fluctuating around. They break down into more general stripes with modulations along one dimension, and then eventually give way to more C4 symmetric patterns resembling that of the charge density. Again, I would like to highlight that across all of these scans of entanglement measure, the charge density is actually the same. It's this square lattice-like arrangement, and this is because we impose by hand this crystalline configuration in the limit that we took. Okay, and this really, if you look at just the spin and pseudospins, there are really complicated textures in both spin and pseudospin space. So the most relevant way of describing this physically is via these unidirectional channels of maximal entanglement. And these have interesting experimental consequences as well. For example, if you have these 1D channels of maximal entanglement, where locally your spin and pseudospin vanish, you can imagine if you have some sort of spin transport experiment where you're injecting a magnon, it's hitting a wall of essentially maximal impedance normally, because you have all your local spins and pseudospins have contracted to a point because of high entanglement. So entanglement can essentially act as some sort of angle dependent impedance for this spin transport. And this is reflected if you calculate the Goldstone mode dispersion for different parameters, you will get a highly anisotropic Goldstone mode dispersion for QX and QY, which would then affect your spin transport depending on the angle. All right, so I just wanted to end with the outlook. So what I've described you is basically a first step in trying to understand these large-scale patterns of spin valley entanglement. You can go further beyond as well, following the liquid crystal analogy. In this work, we considered a very particular limit in which the crystalline charge configuration was imposed. You could consider possibly relaxing that constraint, or maybe due to thermal reasons, where in the high TC literature as well, you could get some transition from smectic or stripe to a nematic, because these stripes would just break off and form orientational patterns. You could also, more interestingly, and this is upcoming work we're doing, focus more. So right now we focused on the entanglement parameter alpha. You could focus on beta, and you could actually design interesting qubits out of this beta. In analogy with what they do with the superconducting phase, you could use this beta as well to devise new kinds of qubits in analogy with transmons. And that's something we're really excited about because it gives you very interesting protection against any kinds of local noise as well. So if you're interested in that, we'd be happy to talk about it. All right, so really viewing this sort of multi-component systems through the lens of entanglement gives you a new way and new opportunities to realize more interesting phases in these sort of strongly interacting systems combined with topology. And with that, I'd like to thank you for your attention and open to any questions. Yes.
So in the case of quantum Hall
Right.
skirmions,
Right.
the old quantum bilayer graphene, there were
Right.
bilayer
Right.
quantum Hall devices where you had
Yeah.
a layer index as well as a spin
Yeah.
index, and the possibility of these configurations
Yeah.
For those systems too. Was it ever considered, or were any of these features?
Yeah, so I think what really depends on whether you could get these sort of entanglement features or not in bilayer graphene or other pseudospin systems is how these symmetry breaking interactions look like. So the reason why we get entanglement in this case, I'm not claiming you could see these in monolayer graphene as well. They really depend on the parameters UP and UZ. If you are in the good region of phase space where this could happen in bilayer graphene, then there is no reason I see why you could not see this. This has nothing to do with whether you have valley or layer as pseudospin. It only depends on the nature of the symmetry breaking terms.
So if I understand it, this is rather like saying whether you have an easy plane or an easy axis anisotropy.
Right.
And in the bilayer quantum Hall effect,
Right.
You had an easy plane anisotropy, and
Right.
the skirmion broke into merons, but you would, in your language, you would call that an entanglement. That is actually, you'd be calling it entanglement between spin and the layer.
Sure. Yeah, that'd be interesting. I mean, I don't know much, but there is no reason why you couldn't get this in as replacing valley by layer, or even in these Moiré systems where Chorn number now effectively becomes a pseudospin. In twisted bilayer graphene, you have these different sub-levels of your effective Landau level picture labeled by Chorn number, and so even that could be an effective pseudospin. So it'd be interesting to explore what that would be. Yeah. Thanks. Other questions?
Yeah. So, yeah, I wonder what's the physical consequence of this phenomenon? That this is not translate directly into beyond the couple.
So what do you mean by does this entanglement translate into spin orbit coupling?
By at the beginning point, your model has no spin orbit coupling.
Yeah.
But if the system somehow spontaneously breaks some symmetry, you get
Right.
a spontaneous spin orbit coupling.
Right.
That will translate into a valley and the spin entanglement.
Yeah, probably. Yeah, I mean, all this entanglement pattern here, if you were to measure pseudo spin density in some, I mean, since you were asking about local order parameter, if you were to take an image like they do in the Yazdani experiments of pseudo spin density, it would exactly show up in that, but you would have but you wouldn't have the same direction of pseudo spin along these lines. You would have textures in both directions, but it is the modulation of the magnitude of the pseudo spin that would show up in this entanglement.
Actually locked with value, which means it's not really different.
Pseudo spin is locked with value. Yeah, correct.
So, you probably mentioned by probability that what I do consider square that it's not like triangle.
Oh, that is just because we have been working with these theta functions and they give you square lattice. You could consider triangular as well, which is probably the more accurate thing to do. Yeah, you could do, but there you would have to do some slightly more. I mean, you would have to change the weights of this basis function. If you just take simplest thing, you'd be a square lattice. But yeah,
Model lines, they are, I think, 3 groups, and they're square lattice.
Yeah.
Flat band models with degeneracy, with Chernobyl degeneracy. One is from O'Neill's group, that's the same Yoli this module. They show that this value Chakroborty gives you 2 degenerate flat band with Chernobyl +2 and -2.
Right.
And that's +1 and -1 dimension. This Chernobyl can give kind of like value. On top of that, the system is it will spin.
Yeah.
And there is that's a square lattice.
Yeah.
And it's a square lattice with 2 bands, not value, but 2 charm bands.
Right.
And another model actually was simultaneously rapid simultaneous. So one from Oscar Rapid,
Right.
another from Eddie Search. It's a single layer quadratic binding with periodic string.
Yeah.
We showed that it has flat binding through 6 position system. The Opta and Eddie they show that both square lattice the same thing works. So those square lattice model I think would be a natural.
Yeah, absolutely. No, I mean that's why we were. I mean, although we didn't start thinking about it in the twisted bilayer or these kinds of twisted material setting, but the fact that you have all these other pseudo spin degrees of freedom in these models is very exciting. Yeah. Yeah, I mean, absolutely. And even at the end, so in this work of course, oh, whoops, did I do too much? Right, so you could consider extensions as well. So I mean, of course, in these cases, not exactly in this situation, but you could consider sort of what they did in the high TC work as well, possibilities of these one-dimensional channels of uniform entanglement, but instead of alpha, look at the conjugate phase beta, and then think of possible Luttinger liquids of this entanglement parameter along these 1D channels as well. Or even if you have more than one pseudospin degree of freedom, you could consider instead of bipartite, tripartite entanglement. And so it's really a whole zoo of these things that you can characterize with this. Yeah, thanks.
Propose to stop here. Let's thank Nilotpal again.
20 minutes late, which will take us till just past